So we've been looking at this f prime of x of 0 equals the limit as h goes to 0 of f of x of 0 plus h minus f of x of 0 all over h. And we were looking at that at our last class period. So first question I want to ask you guys is, what is that representing? So I'm going to just pause the video and let you guys put in the chat what is a way to describe what's going on with this f prime of x of 0. So just type in what it is, and then in a few seconds, I'll tell you, or 30 seconds, I'll tell you guys to push enter. So don't push enter until everybody has a chance to write in what that would represent.
Sorry.
Okay, so awesome. So there's a lot of different ways to define this, but they all pretty much mean the same thing. So f prime of x of 0, that's the derivative of our function f at some x value. And that is equal to, we looked at the limit as h approaches 0 of f of whatever value we're looking at the slope of at that curve, or the instantaneous rate of change. We also talked about that as being the slope of the tangent line. And I didn't continue with what that difference quotient was, but that's what that gives us. Today, we're going to look at finding the function, the derivative of the function f of x, so that we could find what the slope is anywhere on the graph. So let me just read through this, and we'll look at some examples of finding the derivative of a function. So in the last section, we defined the derivative of y equals f of x at the point x equals x of 0 to be this limit that we had just talked about. We now are going to investigate the derivative as a function derived from f by considering the limit at each point x in the domain of f. So only difference here, when we're looking at the derivative of a function, instead of there being a number for that x value, the derivative of the function f of x with respect to the variable x is the function f prime, whose value at x is given the following. So f prime of x, the derivative of f of x, is equal to the limit as h goes to 0 of the difference quotient, which is f of x plus h minus f of x in the numerator all over h. We have to put in that provided a limit exists. If the limit doesn't exist, then the derivative is not going to exist. And we'll talk about that a little bit more in this section. Okay, so we use the notation f of x in the definition rather than f of x of 0 as before, to emphasize that f prime is a function of an independent variable x with respect to which the derivative function f prime of x is being defined. So there's a lot being said there, but basically it's just emphasizing we're looking at f prime of x as being that derivative is a function in terms of x, versus if we look at f of x of 0, that is actually a point. The domain f prime is a set of points in the domain of f for, oops, it's down here, for which the limit exists, which means that the domain may be the same or smaller than the domain of f. Okay, so the domain of our function f could be the same as our domain of our, could be the same as the domain of our original function. Sorry, derivative can have the, okay, let's just stop. I just need to pause and not do 20 things at once. So if I look at the derivative of my function f, the derivative of my, the domain of the derivative of my function could be the same, or it's going to be smaller.
Then r prime?
So my function, if my domain for my function f was something, then my domain for my derivative function could be the same. If it's not the same, then I've had to exclude some values from the domain of my function.
Okay, that's why things go out to zero, right? That's why we make everything go to zero when we're taking the derivatives.
No, so let me show you a case, what I'm talking about. So here, if I look at this function in here, well, I'm just going to draw a picture. So let's say maybe I have something like this. So in this picture, this is hitting all my X values. So let's say that this was f of X. And so my domain for f of X is all real numbers. But if I look at the derivative, I'm actually going to have a problem, and I was going to talk about this later, but I might as well just bring it in now. I'm going to have a problem where this is like a sharp corner. Because if I think about taking the derivative at this point, it really depends on, am I taking that value less than X a little bit? And if I did so, then if I looked at the tangent line at this point, I might get something that looks like this. If I had chosen my H value to be a little bit bigger than X when I was looking at the slope between those 2 points, and I'm getting really, really close, then my tangent line, or this, is going to look like this. So my slope of the tangent line is going to be the same thing as the slope at that point. And so notice that my slopes are different depending on which way I'm coming in on. And so when I would look at the domain of the derivative function, it's not going to exist everywhere. It's not going to exist at, let's say this value is X equals C. So for the domain of this, I have to exclude just that value. Everywhere else, whenever I took the slope of the tangent line at any point on here, or I'm going to have the derivative function, it would work. And so I would have the domain in this case being the negative infinity to C union C to infinity. And so if I'm trying to look for the domain of my derivative function, I want to look first at my domain of my original function if I have it. I know that it's either going to be that, or I might have to exclude some values from that. It's never going to be, though, any value outside of the domain of the original. In that case, that was all reals.
Thank you for that.
Yep. Sorry, sometimes I'm thinking too much in my head. Like I said, I've told you guys before, so I need to just slow down, and then things are shifting. So I'm trying to move things around, and yeah, so. Thank you for the question, because that made me slow down and try to explain that better. And so we'll see in a minute, looking at finding out where a function is not differentiable. And that's what, I don't know if I just said that. So if f prime exists at every point in the domain of f, we say that f is differentiable. So in this case, I would say that it's not differentiable at x equals c. And so we'll be looking at places where a function is not differentiable in a minute. There's one case. Okay, so I wanted to bring in some of the questions from the back of that section. And these are pretty much saying pretty much the same thing, except that notation is a little different. And so if it tells us, let's look at the first 6. And we're not going to do the first 6, but let's at least take one of those and try it. So using the definition, we're going to calculate the derivative of the function in 1 through 6. Then we're going to find the values of the derivative as specified. So I'm going to let you put in the chat, if you're here, I'm gonna pause the video, but you kind of shout out in the chat which number you would like to see from 1 to 6. And we can always do multiple of them. Okay, so we're gonna start, just get warmed up and remember how to do this. But we have f of x equals 4 minus x squared. We want to find the derivative of f of x. And so we know that that's the limit as h approaches 0 of f of x plus h. So that's where we were going in, right? And wherever we saw an x, we're going to plug in x plus h. And so if I do that, I would get 4 minus x plus h quantity squared minus my whole f of x function. So minus, I'm going to put brackets there because that negative has to distribute, 4 minus x squared all over h. And so we want to clean this up by distributing and combining like terms. So I'm going to bring down that limit until I actually evaluate it. And so I have 4 minus, if I distribute out x plus h times x plus h, I'm going to have parentheses, I'm going to have x squared plus 2xh plus h squared minus, so distributing my negative, I'm going to have minus 4. And I'm going to have plus x squared. So we got to just, and this is still all over each. So we're going to need to distribute that negative, and then, like I said, we can combine like terms. So we have 4 distributing our negative into this parentheses, we get minus x squared minus 2xh minus h squared minus 4 plus x squared all over h. So things, if you haven't noticed, always tend to cancel out pretty nicely. We have a negative x squared plus the x squared goes away. We have this 4 minus 4 goes away. If I did direct substitution right now, I would get 0 over 0. So that tells us sometimes we just factor. So notice out of this negative 2xh minus h squared, which is left, we can factor out an h. So let's pull out a single h. Then I'm left with negative 2x minus h all over h. So the h's cancel. Now when we do our direct substitution and plug it 0 in wherever we see an h, notice that we just get back negative 2x. So we just found that the derivative of our function f of x is equal to negative 2 times x. So if we wanted to find the slope now, anywhere on our curve of 4 minus x squared, which we can graph, that's just a parabola that is reflected across the x-axis facing downwards, and that 4, think of it as shifting up 4 units. So we have 1, 2, 3, 4. And we can find the slope anywhere on that curve by plugging in some x value. So if I wanted to find the derivative or the slope of the function f of x at, let's say, x equals negative 1. So f prime of negative 1, I would just go in and plug this in wherever I saw an x in my function. So this is equal to -2 times -1, which is equal to 2. If you look at where x is, when x is -1, if you look at our function here, notice that if we look at the slope there, it's an increasing function. I'm going up left to right. So it's saying that that slope is 2 here. And you can see that the tangent line is increasing, or that slope or that tangent line is 2. If we look at f prime of +1, well, that would give me -2 times 1, which is -2. Which, if you look at it, it's decreasing at that value. Actually, these are symmetrical across the y-axis too. But we could find the slope anywhere on that curve. Okay.
Ms. Lawson,
Yeah.
Professor?
So I knew I'd get this question. And so I thank you for asking it. So question was, I've learned how to do derivatives before without doing all this work as the limit as h goes to 0 of that difference quotient. Can you do that? And right now I'm going to say no. So,
Okay.
but it's something to look forward to, because don't worry, we're not going to have to do this for much longer. So I think either tomorrow or the next day, I'm going to give you rules of how to find derivatives easier than going through the formal definition.
Yes, no, I know. And this gets even longer as we go a little more further. And that's why we use, right, the rest of the rules.
Yeah. So good, we get so tedious, and you guys can see that. And so I just want to make sure, if when I give you guys an exam during class, there will be times where I'll say, okay, use the formal definition of the derivative to find the derivative. Otherwise, if I don't state that, once we get out of these couple sections or this section, then you can use any method. And you would probably use the method I'm going to teach you soon.
Okay. Thank you.
You're welcome. Yep. So there's something to look forward to soon. So let's pull another one of these out. So 4, 5, and 6 were other ones that you guys had mentioned. Same sort of idea with 6 as we would do with 5. It's just 6 is a little more difficult. Don't get caught up because that says theta in there. That's just our independent variable. Okay, so I'm going to have, and I'm going to call it r of x instead of r of s. Actually, no, let's just keep it that way. It's trying to get you familiar or used to doing other variables than x. So we have r of s. Oops. Okay, so our next example, we have r of s is defined to equal the square root. Underneath the radical, we have 2s plus 1. First wants us to find the derivative of r with respect to s. And then we're going to find the derivative of r with respect to 0. So we're going to figure out what that slope, the curve is at x equals, or s equals 0, and r prime of 1/2. So part A, let's just do it here. So we're looking at the limit as h approaches 0 of this r of, just put it here, s plus h. So wherever we see an s in our function, we're going to get This is the square root of 2. I see an S there. So I'm going to plug in S plus H. Then I have this plus 1. Then I have minus R of S. But R of S is this function here. And so I'm just going to subtract off the square root of 2S plus 1. And we're going to put that all over H. And this is what R prime of S is equal to. Okay. If we go in here and we do direct substitution, you're going to get 0 over 0. And we were looking at different tricks on how to deal with 0 over 0. And so this one has a radical in it. And so one of the tricks was that we multiply by the conjugate, a fancy one, the conjugate in the numerator and denominator. Okay, so I need to manipulate this. And so let's multiply by that fancy one. I'm gonna move this over for now. And so that fancy one, and that's the same thing that you would have done in that problem 5, I believe. Maybe not. Okay, so going in here, we have the square root of 2 parentheses S plus H. Let's just distribute that, because we're going to have to do it anyway. So 2S plus 2H plus 1. Conjugate, so change the sign in between the radicals. So plus the square root of 2S plus 1. We're going to do the same thing with the denominator. The whole reason that we did that was so that we could clear our radicals, and we had multiplied that so it was a difference of 2 squares. And so if we square our first term, I'm going to bring down my limit. We square the first term, that would get rid of my radical, which underneath the radical gave us 2S plus 2H plus 1 minus the square of the second term. So I need parentheses here. So if I square the second term, that would just be 2S plus 1. And this is all over H times, and I'm not going to distribute, I'm just going to leave it like this. So the square root of 2S plus 2H minus 1 plus the square root of 2S plus 1. So once we've distributed that negative, we're going to have a 2S minus a 2S, which is going to go away. We would have this positive 1, and then we distribute the negative to that one inside that parentheses here. So that would be minus 1. So 1 minus 1, those cancel. And so notice we just have 2H in the numerator, and we have that factor of H down in the denominator. And so those are going to cancel with each other. And we will no longer have that indeterminate form of 0 over 0. So now when we go do direct substitution, we're plugging in 0 wherever we see an H. So we'll have the square root of 2S plus 2 times 0 minus 1 plus the square root of 2S plus 1. That should have been plus 1. Yeah.
Yeah, and wouldn't it be 2 on top?
Yeah.
In the numerator?
Yeah, thank you. So right here is a 2, and this should have been a plus 1 underneath the radical. So notice that that's going to actually be the same thing. So we can add radicals if they have the exact same thing underneath the radical. And so this is the same thing as 2. So the square root of 2s plus 1 plus the square root of 2s plus 1. Well, there's 2 of those. So there's 2 all over 2 square roots of 2s plus 1. And so notice now those 2's cancel. We have a 2 in the numerator denominator. And so we found the derivative. And our derivative of r with respect to s is equal to 1 all over the square root of 2s plus 1. So now we want to, it asked us to find what the derivative was at 0 and what the derivative was at 1/2. Okay. Let me just pull the screen down a little. So r prime of 0, you're just plugging in 0 wherever you see an s. And so notice that we'll have 2 times 0 in the denominator plus 1, and that's underneath that radical. So that's going to give us 1 over the square root of 1. And that's just 1. So that's telling me that if I looked at the derivative function, or if I looked at the original function at x or s equals 0, my graph is going to be increasing. And it's going to be increasing at a rate of 1 at that value. If I wanted to look at r prime of 1/2, so I just go in and I plug in 1/2 wherever I saw an s. And so in this case, I would have 1 all over the square root of 2 times 1/2 plus 1. Well, the 2's cancel underneath that radical, so we have the square root of 1 plus 1, which is the square root of 2. So I got 1 all over root 2. Normally we rationalize our denominator. We can get rid of that root 2 in the denominator by multiplying by that fancy one again. In this case, it's root 2 over root 2, and we get root 2 all over 2. So the slope there is also positive. So I know that that function is increasing at 1/2. So when I pulled up those examples in front of you from the back of the text, I was telling you that, they all mean the same thing. It's okay. But that is that we have different notation. And so we needed to get familiar with a different notation that you may be seeing. So there are many ways to denote the derivative of our function y equals f of x, where the independent variable is x, and we say the dependent variable is y. So some common alternative notation for the derivative includes, so we've seen that f prime of x. Well, if it's y equals, instead we can say y prime. You might look, this is not really a fraction, but dy you have over dx. This is saying that I have my function, I'm taking the derivative of my function y. The dx is saying it's with respect to the value of x. well, if I don't use y and I use f of x, I could write the derivative of f of x is df all over dx.
I think the screen share might have frozen.
I knew that was coming when I saw the video or when I saw the time. Okay, so let's see.
Isn't there like a du dv?
Yes. So if we had du dv, that would be saying the derivative of your function u. So your function would be in terms of u.
Oh yeah, I remember seeing that one as well, and I'm like, it's not up there. So I was like, there's another way.
Yeah,
Isn't there?
but that's just saying that our function is in terms of, our function is named u,
Oh,
and
okay.
the variable is v.
Okay.
So, hold on, let me just stop so I can get this unfrozen. Pretty much all I'm doing is reading from it right this second, and it didn't work.
Hello. Did she just freeze?
Did I freeze again? No.
You froze for a while, so I didn't know if it was me or like.
No, that tends to happen around this time. So, I had to jump out to get back in, so I could unfreeze it. But it sounds like, it looks like maybe right now it's unfrozen. Part of me is wondering, well, okay, so we are looking at the derivative and the different notation that we could have. We've seen the f prime of x. We've just talked about that it could be y prime, this dy over dx that is representing the function of y. You're taking the derivative of your function y with respect to x. Df dx is another way to say it. D dx of f of x, capital D f in parentheses f x. I don't usually use that. This d little x of f of x. These are more of the ones that I would use in class, and you'll see more often. So let me just read through this really quickly. So the symbol d dx and capital D indicates the operation of differentiation. So it's telling me that we're going to take the derivative of this right here. We read dy over dx as the derivative of y with respect to x, which I mentioned, and df over dx and d over dx f of x as the derivative of f with respect to x. The prime notation, y prime and f prime, this originated with Newton. So Newton came up with that. The d over dx notations are similar to those used by Leibniz. So these were two mathematicians that came up with the derivative, but they came with different symbols. So the symbol dy dx should not be regarded as a ratio. So don't think of that as a ratio. That's just a function. It is simply a notation that is denoted as a derivative. Okay, so to indicate the value of a derivative at a specified value x equals a, we use the notation f prime of a. So we were looking at this at the last section, finding the derivative at a particular point. Or we can rewrite this as dy dx with a vertical line x equals a. Or df over dx with a vertical line x equals a. D over dx, f of x with a vertical line x equals a. Those are all meaning the exact same thing. So that being said, let's look at one more example. And then we'll stop for the day. So I really wanted to do this one more problem, dy over dx. This is saying we're taking the derivative of y with respect to x at x equals √3. We're given that our y value is equal to 1 minus 1 over x. But I looked down at the time and we are all out of time. And I know I've been running over lots of days. So this is where we are going to pick up tomorrow in tomorrow's lecture. So you're going to have to hold on and wait until tomorrow, and you'll see what that, how to do that tomorrow if you can't do it already. So great question. So this is just saying we could have called this function f of x instead of y equals. And notation wise, basically, we're just finding the derivative of x. And in this case, with respect to when x is √3. And so we could do it with a limit like we were doing it last class period and from 3.1, finding the derivative at a particular point. Or we can look at it by finding the derivative of the function and then plugging that value in wherever we see x.